Hey guys, I'm sorry I can't be there today. I am staying home with Zeke because he is sick. I did want to say that if you had some homework questions on the 9.3 worksheet that I would have been checking today, you can check Blackboard and content. I worked out a couple of the questions in first period, and that's posted in the notes that were posted yesterday. They're the 9.4 notes. Also, the video that I'm about to make here is basically the lesson that I did yesterday in first period. So there is a PDF already made and posted in Blackboard in content. So check that out if you want an already, filled out version of these notes. Before we start, I want you to actually try to do the warm-up that I had because I think that it actually helps you with getting into the lesson. Okay, so this warm-up is going to require a graphing calculator, so please get one. And obviously, please pause the video when it makes sense to pause so you can write things down or actually do things. What I would like you to do is graph each of these equations in your calculator, and I want you to look and see what the graphs have in common and then also what the equations have in common. And I'm hoping that there's something that you will notice that's going to help us with our lesson today. So pause the video if you have not already. Go ahead and pause it and graph these functions and see what they have in common. Hopefully you found that these have, that their graphs kind of have this slant thing going on. They also are kind of symmetrical. The slant is like an asymptote. Instead of just having a horizontal asymptote and a vertical asymptote, they almost like approach another line that's like diagonal. So it's like a diagonal asymptote. And then if we look at the equations, you'll notice that all of them, the numerator is bigger, but specifically the numerator is bigger by 1 degree. So we know when the numerator is bigger that there's no horizontal asymptote. And then this is a special case. There's no horizontal asymptote, but because the degree is exactly 1 bigger, it creates a slant asymptote. So there actually is a way to find the slant asymptote. It's a lot more involved than finding horizontal and vertical, but it's helpful to find it so that you can sketch problems that might have it. So we're going to do 3 examples. All right, this is lesson 9.4, and it's about slant asymptotes. So first we need to talk about what it is and when it happens, which we kind of already did, but let's write it down. So slant asymptotes happen when the degree of the numerator is exactly 1 more than the degree of the denominator. It actually makes a lot of sense because remember, asymptotes, like horizontal asymptotes, happen when you essentially think about plugging infinity in and what happens to the y value when you plug a really, really big number into x. So this is still similar. It's like what's the y value approaching when you plug in a really, really big x? Instead of approaching one single number, it's going to be approaching a line that's like slanted. So the way we're going to find slant asymptotes is actually by dividing these rational functions and simplifying them, which I'm pretty sure you're not going to like, but we still have to do it anyway. We're going to have to do long division. Now you might remember synthetic division from Algebra 2, which you're totally welcome to do synthetic division if you're dividing by something linear, like this one. This one's linear, so you could divide this one with synthetic division if you remember how. But you can't divide with synthetic division if you're dividing by something that's a bigger power than just 1. So if you're dividing by a quadratic or a cubic, you have to do long division. So I prefer to do long division all the time because it works every time. Okay, so I actually did a long division problem on the side of the board with regular numbers just to kind of refresh our memory on how long division works in general. But it's really similar with polynomials. but you're always looking at the first terms. So I've got x going into x squared. So like x times what gives me x squared, and that is x. Or you can think of it as x squared divided by x is x. And then just like long division, you're going to take that x and multiply it. I'm going to point at it with my lightsaber. So I'm going to do x times x plus 1. And that's going to give me x squared plus x. So x times x is x squared. X times 1 is x. But don't forget, you have to subtract this entire thing. That gets people in trouble sometimes, because clearly these two terms cancel, but we need to distribute this minus sign in. So that's actually a negative x minus x. So right there we have negative x minus x, which is going to give me a negative 2x. And there's nothing over here to bring down, but I like to put placeholders in sometimes. Well, not sometimes, but pretty much all the time. So if I was missing an x, I would put 0x. So I'm going to bring that down. And I'm going to do the same thing. It's always the first terms. So negative 2x divided by x is negative 2. So put the negative 2 up there. And then I'm going to multiply this negative 2 times x and times 1. That's going to give me negative 2x minus 2. And when I subtract that, the 2x term is going to cancel. This minus is going to go in, so it's actually going to become a plus 2. And so I end up having 2. And 2 cannot be divided by x, so that means that 2 is my remainder. Just as a reminder how to write this with a remainder. So x minus 2 is basically like the whole number part of my division. And then the 2, the positive 2 is the remainder. So I write it as 2 over x plus 1. And that just comes from the remainder divided by the original quotient right there. So x minus 2 and then the remainder. I actually don't really care that much about the remainder, because the slant asymptote comes from the part that is right here, just the quotient part. So not the remainder, but the quotient part. So x minus 2, like y equals x minus 2, is my slant asymptote. So because y equals x minus 2 is a slant asymptote, it means that as x goes to infinity, the y values are going to approach whatever x minus 2 is. It'll actually approach that line. So I'm going to try to put a graph in here that shows you the original function and then also shows you x minus 2 so that you can see what that looks like. Okay, so here you can see the red function is the original function, the rational one, and then the blue function is the slant asymptote, x minus 2. So you see that as x goes to infinity, the y values get closer and closer to that diagonal line, and that is a slant asymptote. So I think it probably would be helpful to do a couple more examples. I want to do one more example that involves finding a slant asymptote when we're dividing by something that's not linear, and then also I want to do an example of sketching. Okay, example 2. Let's suppose I asked you to determine if this function has a slant asymptote, and then if so, actually find it. We have f of x equals 2x cubed plus x squared minus 8x minus 4 over x squared minus 3x plus 2. Alright, I can tell this is a slant asymptote because of the degrees. The degree of the numerator is exactly 1 more than the denominator, so I know that it's going to have a slant asymptote. The way I'm going to find it is by doing long division And this problem might look intimidating at first since it is a cubic and a quadratic, but it actually ends up not being too bad. So give it a chance. Just follow the process. All right, so I start off by doing the first two terms. So 2x cubed divided by x squared. Or how many times does x squared go into 2x cubed? Or you can think of it as x squared times what is 2x cubed. So x squared times 2x gives me 2x cubed. And then I'm going to multiply the 2x times everything that's over here. So when I'm dividing, I really only pay attention to the first two terms. But when I'm multiplying, I need to multiply by the entire thing. So 2x times x squared is 2x cubed, and 2x times negative 3x is negative 6x squared, and then 2x times 2 is 4x. And please don't forget I'm subtracting that entire thing, so I like putting parentheses around it so that I don't forget to distribute that minus sign. So that's going to cancel. You're going to have x squared plus 6x squared, so you have 7x squared. And then you have negative 8x minus 4x, which will be negative 12x. And then I'm going to bring down the minus 4. So again, please feel free to like pause and rewind and rewatch things if you're trying to figure out where things came from. Now I start the process over again with the first two terms. So 7x squared divided by x squared is 7. And then once again, I'm going to multiply the 7 times everything that's over here. So 7 times x squared is 7x squared. 7 times negative 3x is negative 21x. 7 times 2 is 14. Again, don't forget to subtract the entire thing. Distribute the minus sign. If I add these together, that cancels out. It's a negative 12x and then a plus 21x. I think we get 9x. And then this is going to be a negative 14, so I'm going to get minus 18. At this point, I notice that the 9x can't be divided by x squared, so this is my remainder. If I'm writing the entire function out, I would write 2x plus 7 plus 9x minus 18 all over x squared minus 3x plus 2. But if I'm just asking for the slant asymptote, all it is the actual like whole thing that was divided all the way up here. So it's y equals 2x plus 7. That's the slant asymptote. One thing that I do need to bring up at this point is domain, because I could ask you for the domain. Now, for every single function, the domain of a function is all real numbers unless it is undefined somewhere. So all I really care about is the denominator of the function, the original function, because wherever this is undefined is what is going to determine my domain. So if I factor this, that's x minus 2 and x minus 1, which means that my domain is x such that x cannot be 2 and x cannot be 1. So I don't really even care if it's a whole or if it's a vertical asymptote. It doesn't matter. Wherever the function is undefined is going to cause a problem for the domain. So I just am looking for where the denominator equals 0. Okay, now we need to put this together with the things that we've talked about before, which is actually sketching the graphs. And this is the last thing we need to talk about in this unit, so we're almost there. If I'm asking you to sketch the graph, we're going to kind of walk through the same process that we walked through on Monday. We'll start with horizontal asymptote. So you'll take a look at the degrees. Notice the degree is bigger on the numerator, so that means there's no horizontal asymptote. However, I do want you to notice that even though there's no horizontal asymptote, the numerator is exactly one more. Like the degree of the numerator is one more than the degree of the denominator. So that means there is a slant asymptote. I don't know what that is yet. We can figure it out in a little bit. Let's go ahead and factor the numerator so we can see if anything cancels out and see if we have any holes. So the numerator factors into x minus 2 and x plus 1. And notice there actually is nothing that cancels out, so that tells me that there's no holes. Sometimes that's good to make a note of, just so when you're sketching you remember. So no holes. However, there is going to be a vertical asymptote coming from my denominator there. So the vertical asymptote is going to be x equals 1. And if you remember, where the numerator is 0 is going to be an x-intercept. So the numerator is going to be 0 at 2 because of this one right here. So 2 comma 0 and then negative 1 for this one right here. So I have a lot of information to go off of. The only thing I need to find is the slant asymptote, and then I'm going to need to figure out some points. So I'm still going to basically do this the same way that I did the original ones that we did earlier this week. Okay, let's do this process. If we were doing this in class, I would have you do this problem by yourself. So I would encourage you to pause the video and actually try to do this long division problem by yourself to make sure that you've got it. No, really, go ahead and pause the video and try it. All right, so x squared divided by x is x. And then I'm going to multiply x times x minus 1. X times x is x squared. X times minus 1 is negative 1x. Please be careful with subtraction. When I do that, these two cancel. That actually cancels as well because it's going to be a negative x plus an x, so it's 0. I'm going to bring down that minus 2. So I get negative 2, and negative 2 cannot be divided by x, so that's actually my remainder. So this one was actually pretty easy. If I had to write the function out, it would look like this. So actually, like the original function, just to be clear what's going on with the remainder thing, this is the original function, and it actually equals this. Like they are equivalent expressions. But if I'm just looking for the slant asymptote, the only thing that matters is the whole number part. So my slant asymptote is y equals x. Just that basic equation. So I'm going to take all of this information that I have, which is that the slant asymptote is y equals x. The vertical asymptote is y equals 0. My x-intercepts, sorry, I think I lost my slant asymptote. There it is, y equals x. Let's put all these things together on one graph, and then we're also going to have to plot some points to kind of see the shape. So sometimes you have to plot more points than you would otherwise without slant asymptotes. Let's try it out. All right, so I'm kind of just doing a rough sketch here, but let's go ahead and put on there what we know. We know that there is a vertical asymptote at 1, so I'm going to go ahead and put a dotted line there at 1. I know the slant asymptote is at y equals x. That is a line, and that's, if you think about y equals mx plus b, it has a y-intercept of 0, and then it goes up 1 and over 1. So it's going to kind of look like this. So I'm kind of just imagining going up 1 and over 1 with that. So it's not perfect, but you get the right idea. Let's also put down our intercepts that we found, our zeros, the x-intercepts. So there was an x-intercept at 2, which is here. There's an x-intercept at negative 1, which is here. So we kind of see where our functions are going to be sitting, but we really need to find some more points. So on this part, we can imagine the graph's going to kind of look like this, but we probably need a point over here and a point over here. So I would suggest maybe plugging in 0 I'm plugging in 2 or 3. I'm sorry, -2 or -3, whichever one you want. So we're going to make a table of values. We need to plug in a couple of points on the left of the vertical asymptote, and then also the right of the vertical asymptote. So I'm going to plug in 0. Here's my original function. You're welcome to plug it into the original or into the factored version. But if I plug in 0, 0 minus 0 minus 2, and then 0 minus 1, it's going to be -2 over -1. So that's going to be 2. So I'm going to go ahead and add that point to my graph, 0, 2. And then let's maybe go ahead and do -2. So I'll plug -2 in, and just to save a little bit of time in writing, let's assume like we plug -2 into here, and that's going to give you -1 1/3. So I'm going to kind of like approximate that on here. And I'm going to go ahead and draw my graph. So it kind of hugs the asymptotes. And it's kind of curved. Mine looked kind of funny. I'm going to try it again. Still kind of funny. Oh well, get the idea. Let's plug in a couple of points on this side of the vertical asymptote. So I would suggest that the thing that's going to be a little bit hard, we really do need to plug something in between these two, between 1 and 2. So I'm going to plug in 1.5. And when I plugged in 1.5, I got -2.5. That's about there. And then I also plugged in 3. And when I plugged in 3, I got 2. So again, we kind of see the mirror image of the shape right there. So that red graph is the graph of this original function. If I asked you for the domain, you would basically be looking at where x is all real numbers, except x cannot be 1, because that's where we have that vertical asymptote, which is where it's undefined. And that is everything you need for this lesson. I do have to say I'm pretty bummed that I'm missing the mathlete versus athlete dress day, because I had a really perfect shirt for today. Because asymptotic high fives are amazing because the fun never ends. I hope you guys have a good day. I will see you tomorrow, and we will be basically kind of wrapping up all this stuff. The test is going to be on Tuesday of next week, because that's when we have our double even day.